Hi, you may notice that the title is slightly different from the agenda. I'm Tom Talpey. I'm an architect in the Microsoft Windows Server file sharing team. I've been to OpenFabrics for many years in various forms around RDMA and remote file storage using RDMA. So I'm here today to actually kind of dive from remote storage for that layer into the RDMA layer, into the platform layer, and finally into the verb layer. So I'm going to sort of give a full stack picture here, and I got 25 slides to deliver in 30 minutes, so it's going to go kind of quick. If you've seen this before, you're not imagining things. This presentation I first gave at, a version, this has morphed over the months, at the SNIA Storage Developers Conference last fall, and again at the NVM Summit back in January. And it represents an ongoing discussion, all right? This is a proposal, ideas, wacky ideas from Tom Talpey at this point, and intended to sort of drive the discussion, all right? So I hope you enjoy the tour here. Here we are. We'll begin with a problem statement. Provide applications, upper layer applications, with remote access to non-volatile or persistent memory storage at ultra-low latency. The key is the latency, right? We know how to access remote storage. Do we know how to do it at low latency that matches the storage medium? Second, to examine the storage protocol and the RDMA protocol extensions, to examine the possibility of these extensions in support of the application's workload, right? What do the applications want to do? What do we need to provide? And finally, to explore the implications on RDMA implementations. That's what I'm adding here. I think you'll be interested. All right, the heck with this clicker. All right. RDMA-aware storage protocols. I'll just set the stage briefly. I consider the ecosystem to be enterprise or private cloud capable storage protocols, all right? We're not talking about block protocols. We're not talking about special purpose protocols. We're talking about things that are deployed at scale in enterprise environments, all right? And that's what I do for a living, and so maybe that's part of it. But I define them as scalable, manageable, and broadly deployed. They provide services inherently such as authentication, security, and by security I mean both integrity and privacy, all right, encryption as well as signing. They natively support parallel and highly available operation, okay? How they do this is all outside the scope of what I'm going to talk about, but they set the playing field. Examples, SMB3 with SMB Direct, that's my baby these days. SMB Direct is the mapping of SMB3 to RDMA. NFS RDMA, that was my previous baby, and that's the mapping of NFS to the RDMA protocol stack. ICER, iSCSI, RDMA, and others exist, right? SRP, Ceph, Lustre, other protocols. But I'm just going to try to stick to these three as examples. And you've seen this before. I'll skip a few RDMAs or review specific things, but storage latencies are decreasing. The write latencies of these storage protocols that I mentioned on the previous slide are currently in the 30 to 50 microseconds via RDMA. They're a good match to HDD and SSD storage, right? That's way less than HDD and about the same as SSD. They're a stretch match to NVMe, right? NVMe has local storage on the backside of a server, which is in the 10 to 50 microsecond range. PM, persistent memory, not so much, right? 200 nanoseconds, right? Less than a microsecond, right? That's not so good. That's a huge cost to traverse the network. And you can see on the picture, there's order of magnitude drops as we go between these four technologies. Storage workloads additionally are traditionally highly parallel, and that's just an observation to bear in mind for a sec. But workloads are changing. Right, replication, right? It doesn't count to make a local copy anymore. You have to make 3 copies in remote error domains, separate error domains. A local copy really means nothing in terms of storage today. So write latency becomes the critical parameter to reduce. It's all about write latency in these environments. This is just an example that shows you how this happens. The writes greatly multiply the network I/O demand. So the remote problem actually gets bigger as you enter this environment. It's not just, I want to send it once. You have to send it multiple times. They must be replicated and durable. In some cases, erasure coding must be calculated, but we'll ignore that just for a moment. Let's say a write comes into that guy on the right. He then has to replicate it to a bunch of peers, right? So there is the latency of the write, but there's the latency of all the replication writes that he performs in the background. Finally, he's going to compute a bunch of erasure codes. These are not so latency sensitive, but nonetheless, they greatly magnify that backside network traffic. So all these copies must be made durable before responding. So the latency of both the red arrow and the green arrow are important. Reads are small and random. They're latency sensitive, but the larger ones are more forgiving, and it's primarily larger ones that you see for reads in these environments. It's used for recovery and rebuild. It's used for loading a cache, things like that. There aren't a whole lot of small random reads going on in these types of environments. A third contributor, or is this the second, to latency are the APIs themselves. And I just want to mention this in regard to what Doug was talking about and what others have talked about today. APIs also shift the latency requirement, and they sort of raise the bar on the latency. Traditional block and file APIs are pretty much parallel, right? They support async I/O, they have multiple operations in flight, they have very deep pipelines. Memory mapped and persistent memory aware APIs are not very parallel. They're effectively a load store expectation, and as Doug sketched, non-blocking, right? The CPU itself will block and wait for that read to terminate or for that write to be accepted by the first stage in the memory pipeline. So they're not parallel, right? They block. There's one thread, one write, that's it. Memory latency is important with a possibly expensive commit that adds latency. And I'll make the observation that local caches can improve the read, right? They can improve the load part, but not the store part, because that write has to be right through. It has to go all the way to these multiply replicated domains. So you can't hide the write. You can hide the read. You cannot hide the write. Okay, let's start at the top. Many layers are involved. We have the storage layer at the top, SMB3 and SMB Direct, NFS, PNFS, NFS RDMA, iSCSI, and ISER, right? These are storage protocols up at the top. They flow through RDMA layers, iWarp, Rocky, Rocky V2, InfiniBand. And they reach a server that has an I/O bus, right? That NIC is sitting in an I/O bus. There might be a storage adapter in an I/O bus. There might be memory on the other side of that I/O bus, right? So there are actually multiple protocols as we move down this stack, and they all need to play end to end. You've seen this, so I'm not going to say much about it, but all the protocols that I mentioned just now have a pull model for write. They send a request. The server then pulls the data from the client when it's ready for the data. It sets up and then pulls the data, performs the write and replies. Okay, 2 round trips on the network. One for the request and response, one for the read that occurs. Writes are a little more, or reads rather, are a little more efficient. They result in an RDMA write, okay? And reads are actually pretty good. But they're still, those little lightning bolts are still interrupts to the processor. There is a server process waiting for a request. It performs the request programmatically and responds. And so those little interrupts add I/O latency. There's a good reason, however, for this type of transfer. It's more secure, and surprisingly, it performs better. When you have a process that has a queue of work, it behooves you to queue data to it. Instead of jamming data down its throat, you place the request in its queue. It's a small request. It then allocates the memory when it's ready, pulls the data, and surprisingly, it improves performance quite a bit. The push model is very difficult when you have a process on the server. I mentioned this. There are several contributors, but the question is, can we reduce or remove all of those above latencies when we're dealing with persistent memory on the remote? So, this is kind of the first phase of the change that I'll propose. I call it RDMA push mode. It's push mode for writes. It's pull mode for reads. But we'll call it an enhanced direct placement model. And those two red boxes, or boxes with red objects in them, are the key. Instead of making a read request per operation or a write request per operation, the client will request server resources. Will basically request to map a chunk of persistent memory, be it a file, a volume, or just a raw DIM. It doesn't really matter. Some sort of map remote region type operation. The server will pin and register the memory. Actually, maybe it doesn't pin it. It doesn't matter. It registers the memory and returns a handle to the client, which the client will then use to perform RDMA to the server. We've reversed the polarity, if you will, of the RDMA operation. So a client write will be an RDMA write in this model, and a client read will be an RDMA read in this model. It can go in both directions, read and write, and there are actually no requests of the server. You'll notice that there are no lightning bolts on the server side here. Nothing's happening. The server is basically just set up the I/O, and the CPU is doing nothing here. This is all happening below the covers at the RDMA layer. However, these guys up here at the top are the protocol, SMB, NFS, ICER, whatever. And I'll just speculate a little on what that would look like. The client will occasionally update the server, right? If it's scribbling on data, it needs to tell the server that the data's become dirty from time to time. Metadata updates, timestamps, things like that, size, file size. And the server as well can call back to the client basically asynchronously. The server can recall, revoke to manage its resources, whatever. Maybe the server allocated too much memory or too many resources to the client and needs to recall them. This is very similar to the way the protocols work today. All these upper layer protocols do recalls at the file layer. So now we're going to be doing recalls at the slightly lower layer. And of course, the client signals the server by closing when it's done. So there's still, the existing upper layer protocol is still there. It just stops doing anything in the middle when the client takes over with RDMA. So if you will, this RDMA transfer kind of slides under the existing protocol in this model. A little bit of hypothetical thinking. What would these three storage layers look like if they had push mode? In SMB3, the operations actually look almost the same. It's just that they sort of change layer, if you will, by moving from the SMB3 layer down to the RDMA layer. The setup is a new create context or an FS control to register and take a lease, to take ownership of the file. The write and the read are direct RDMA accesses by the client. The commit is either a flush or some sort of, I'm just about to mention, RDMA level commit operation. The callback is an existing server callback. We have oplocks in the SMB3 protocol that do this, and lease recalls. And the finish is a close or a lease return, basically some sort of return to ownership by the server. NFS RDMA is almost the same thing. A new NFS v4 operation. NFS v4 doesn't have FS controls or create context, so it probably needs a new operation to perform this registration and offer a delegation. The write and the read are the same model. The commit is the same model. The callback is basically the same model. NFS v4 is a slightly different method, but it follows the same thing. ICER is a little more complicated. I won't claim to be an iSCSI expert, but it's a fairly straightforward application of an existing so-called data mover primitive in iSCSI. Write would become, setup would become a new operation to register and advertise the buffer. A write would become something that might be defined as an unsolicited SCSI in operation. Right? In iSCSI or iSCSI in general, you have solicited versus unsolicited, data in and data out. And so there's currently no definition in ICER for an unsolicited data in operation, but it could be added. It's a fairly straightforward concept. It would implement RDMA write within the initiator to the target buffer, and there would be no R2T processing. There would be no actual exchange of the R2T message to transfer the data. It would be entirely under the control of the initiator to perform that RDMA write. Read would be an unsolicited SCSI out operation, which would implement RDMA read within the initiator, once again, and also would have no target R2T processing. So the target would be silent during this whole thing. All the operation would be on the initiator. Commit would probably be a new operation. It might be something like a force unit access processing. I'm not sure. A SCSI expert would have to weigh in on that. Callback might be a unit attention. I don't know. These are just some ideas. Okay? All right, let's move a layer down. RDMA protocols. Unfortunately, RDMA does not provide any guarantee, any remote guarantee of durability. RDMA write alone, I'm sure many of you are aware of this, is not sufficient for this semantic. Some NICs, completion at the sender never means that the data was physically placed in memory. Never. Some NICs give stronger guarantees. Some NICs will say the data has actually reached the remote NIC. Other NICs will acknowledge a write when the data was buffered and is being sent. The notion is at the verb layer that a write completion means you can reuse your buffer again, right? It may or may not reach the destination. You'll get an error eventually, but you don't know exactly when it reached the destination. You definitely don't know when it reached memory on the destination. You only know that it reached something called the consistency guarantee, so that the CPU and the NIC both see the same data, all right? Lands in a cache in general, some sort of cache, or some sort of snoop domain. Very subtle and important difference. As well, that's the sender side. Processing at the receiver side for an RDMA write means only that the data was accepted, right? That the NIC got it, right? Not that it was sent on the bus. The NIC may have queued it to be sent on the bus, but it hasn't actually been sent on the bus. Segments can also be reordered by the wire or the bus. These are all tagged segments. So only an RDMA completion at the receiver guarantees placement, and a completion implies CPU processing, which is what we're trying to avoid. But even then, placement does not equate to commit, does not equate to making it durable. That's a second step. So there's no actual commit operation implied by RDMA write. Certain platform-specific guarantees can be made. The RDMA read after RDMA write trick. You read the last byte. That says it's flushed through all the buffers. It won't work. Modern Intel CPUs will still put it in a cache. They won't necessarily move it to memory. That's a platform-specific behavior that the client can't know. This is a real pickle. How do we do it? I think there are two obvious possibilities. And everybody thinks of the first one once. They say, put a push bit on RDMA write. Yay, we're done, right? But it doesn't work. There's a few problems. It significantly changes the RDMA write semantic, right? It means that you have a blocking operation. RDMA write starts became a blocking operation. You have to wait for it to push, right? That's really hard. Also, RDMA write doesn't really have an ACK. There's a transport level ACK, but there's no real write ACK and in the protocol. And so as a result, how do you implement this? What do you wait for? It requires significant change to the RDMA write hardware design, and especially to the initiator work request model. If your RDMA writes block, then they'll block the send queue. If they block the send queue, you really change the behavior that the application sees. So you have to approach this very carefully. I argue that it's very undesirable. It sort of changes everything. The second idea is to define a new operation that I call RDMA commit. It's a new operation, flow controlled and acknowledged, kind of like a read or an atomic. It's explicitly acknowledged, right? You send the request, it processes on the NIC and comes back as a result. Its disadvantage, of course, it's a new operation, but its advantage is it's a very simple API that matches very well to the APIs that we're examining for local access to persistent memory, mapped file APIs with a flush, for instance, where you do the loads and stores, they're ordinary loads and stores, and then you commit. You do this thing called optimized flush that Doug described. Operating on one or more regions, preserving the existing semantics, so you minimize the RNIC implementation change. I think this is the way to go, so this is where I'm going to explore. So we call it a new operation. We implement it in any protocol we like. It's actually a very high-level requirement, if you will, for an operation. The initiating RNIC provides a region list and other commit parameters under control of the API. The receiving RNIC queues the operation and processes it in order, right? So previous RDMA writes are processed before this commit operation, just like existing RDMA semantics. The operation is processed much like an RDMA read or an atomic, where the NIC itself processes it without interaction of the local CPU. And it's therefore subject to flow control and ordering, which is important, okay? Ordering. The RDMA pushes the pending writes to the targeted regions. It basically flushes its buffer. It additionally pushes through the bus of the platform and performs the commit, right? Today in Intel CPUs, that requires this magic instruction called pcommit, actually CL flush and pcommit. In the future, hopefully we can provide it via PCI Express. I'm going to explore that in a minute. And the RDMA responds only when durability is assured. So the API contract is, you reply only when the commit is done. There's a few other semantics that you want to wrap around RDMA commit, though. The first is some sort of atomically placed data after commit. And we call this the log pointer model, where you write a slug of data, and then you want to shift the pointer to point to the slug of data, right? And you want that second write to occur only after the first write was completely properly placed, right? It's basically you've written a circular log, and you're going to update the pointer to the circular log. Second, immediate data. Every once in a while you want to signal that upper layer that some of this is happening. Immediate data is a very convenient way to do that in a tiny little packet. So immediate data is something to consider as a secondary payload to the commit. And finally, maybe an entire message. Maybe your upper layer actually wants to send a whole chunk of data, more than the immediate data can hold. And maybe additional processing, e.g. an integrity check. Let's say the client, the sender, wants to be sure that the data landed the way he sent it. So additional processing may be requested. So all these things are very desirable, but they're sort of shades of new semantics on top of this commit. So they may be best implemented in an ordered following operation. Right? We may want a small sequence of operations that can be put together by the initiator in a clever way to implement things accurately without having this huge overloaded decorated operation. The decisions for which ones of these other semantics we choose, though, will always be workload dependent. Some workloads will want them, some workloads won't, some workloads will prefer one, prefer the other. I think there's going to be quite a bit of dialogue here. But a couple of quick observations. The small log write scenario, I think, will be very common, in which we write commit, write commit, write commit, write commit, write commit, right? That's the only thing that appears on the wire, right? And I think we need to think that through and make sure that works well. Bulk data movement, that may permit batching. So batching might be an interesting thing to look at as well at the protocol level. Why didn't this advance? There we go. Okay, let's say we have this new RDMA thing, and now we want to extend the API. This is concept, but I think there may be new platform-specific attributes for a memory registration to indicate things about the persistent memory, right? The memory registration, as I mentioned earlier in a question I asked actually, is a local thing. It's not a protocol thing. It's just a local behavior. It's a local convention. It's a verb. And so how do we decorate that local convention to tell the NIC what to do with these regions? So I think that these are server-only or target-only decorations. But I think they pretty much sit here in these two arguments, PM type and mode, where PM type, minimally, PM type can include the type of PM. It could be plain RAM, not persistent. It could be PCI Express resident, could be a device in the PCI Express bus. Any other local platform specific processing. It may be type A or type B of persistent memory. The mode indicates the disposition of the data, whether the handle is read-only or write-only, but also whether it's cacheable after the operation. There's some workloads where you really don't want the remote CPU to even know that this data existed. There are others where you want to push the data up. You want it to be processed promptly. And a lot of these upper layers are concerned about the caching policy of the data. But that's a local matter. It's local to the platform that owns this data. The peer sort of has no business telling that platform what to do. So we may decorate the API a little. And I'll make the observation that if we get the extensions right, transparency is possible when completions are still in use. When you're sending interrupts and you're telling the CPU to do things, then the driver, if you will, the NIC driver, can piggyback some of this behavior on that CPU signal. And there can be certain advantages to transparency here. The most obvious one, it's not on this slide, it's on the next slide, But, oh, it is right here. Ordinary receives. One obvious one is that a send-receive model could be terminated in persistent memory. And you could have messages going to persistent memory durably, with perfect transparency. So there are certain tricks we can play locally that mean we don't have to extend the protocol at all. And that's sort of phase 0 or phase 0.5 of this idea. I'd love to explore that down the road. Yeah, this platform-specific extension is something that we will need, I believe, for PCI resident devices. Currently, as I mentioned, the Intel processor requires an instruction, pcommit, CL flush and pcommit. We want to avoid that. We don't want to interrupt the processor at all. We want this to happen on the PCI bus. There's no PCI bus instruction for this. There's no message on the PCI bus for this. It would require some sort of extension. Maybe it's a new PCI message. Maybe it's an adaptation of existing PCI messages. Maybe it's just some sort of simple platform-specific magic that can be played. If that local NIC knows how to make that magic incantation, more power to it. If he doesn't have to interrupt the CPU, great. But it would perform the equivalent of the CL flush opt and pcommit that Intel currently require. And I'll remind people that if the NIC is on the memory bus or it's otherwise within the CPU complex, maybe it's on the motherboard in the North Bridge, close to the North Bridge, then many other possibilities exist. But whatever they are, the most desirable extensions are standardized ones that all adapters can implement, right? So we get the best ecosystem when that occurs. All right, I'm running low, so I'm going to keep accelerating. Latency expectations of this model, this push model, if we can build the upper layer push model, the RDMA commit model, and the PCI Express protocol, right? We take those three pieces and we put them together. I believe we can get to single-digit microseconds, no problem. Sub 5, 2 to 3 plus the data wire time. It's basically the commit time, which is managed by the NIC and dependent on the platform and the payload, how much data you've sent. But, I'll mention this is an order of magnitude improvement over today's transfer mode, right? Which we're currently in the 30 to 50 microseconds, I think I mentioned earlier. So we're in the 3 to 5 microsecond order of magnitude. It's not every day that you can see an order of magnitude shift in the storage industry, right? Pretty good, right? So remote read is also possible. I'd expect roughly the same latency of write, but without the commit. Right? We'd still get 2 trips on the network. We'd still have a request and a response. But we wouldn't require the commit, right? When we push, we send the data, we commit, and we get the response. There would be no server interrupt, 0 server CPU overhead once the extensions were in place. And there'd be a single client interrupt, which we could moderate and batch. So we could get really deep parallelism with multiple channels, with good flow control management, deep pipelines. That'd be really cool. A lot of IOPS in this picture. But I want to mention a few things specific to the community here. There are implications on the RDMA layers beyond the protocol. And I think they're kind of important. Remote persistent memory access is in effect itself a new upper layer protocol, right? We're doing reads, writes, and commits across the wire. It's a fairly simple protocol at its base, but it will have RNIC and verb implications. The primary ones I see will be the workload, if you will, of RDMA operations, right? Very different from the workload we're doing now. For instance, there won't be any sends and receives in this picture, right? Resources, and I'm going to drill down on that, and memory registration semantics. All these 3 things will change in the RDMA picture. And so I'm going to speculate and explore a couple of ideas. And if you throw tomatoes, I'll know I'm way off base, but I think it's important to at least mention these. I'm going to do it a little informally. Okay, so the push mode workload, this is the RDMA workload, the RDMA ops you see on the wire from a PM, from a persistent memory workload. The push mode is very simple. There's a one-time setup which connects, authenticates, and creates these regions, all right? Very simple. Following that, it's pure RDMA write, RDMA read, and commit, right? And that's it, nothing else. If you have that upper layer that occasionally does a little bit of metadata or something like that, well, some interesting things sprinkle in, but primarily you're moving data. You're a data mover. It's a one-sided workload. All the programmatic activity is on the initiator, is on the client. It isn't really a client because we don't have a client-server model. We have a client-to-nothing model, right? It's a one-sided model. So one side is, the target side is nearly silent, right? It's just sitting there, except for the occasional metadata update, recall, etc. So our performance workload is radically different, right? There's only one active entity here. Is this a return to the storage adapter model, where the CPU on the target really doesn't matter anymore? I think my friend Stephen Bates, who was supposed to be here to co-host the BOF but couldn't be here for family reasons, calls the CPU the compute peripheral unit because all it does is sit there and set up the connection, and then it doesn't have anything to do. So I think this is an interesting implication. I think it will change the way we build systems. I'd love to build a system with no CPU. Can I say it that way? I think you could do it. Second thing, resources, RDMA resources. There are 2 slides for this because I got a lot of things to talk about. First of all, we're going to be registering large regions, like really large regions, the entire DIM, or at least really long scatter lists that map to a file. Right? Let's say we have a virtual hard drive with a bunch of sectors all scattered around because the file system did that. Right? We're going to have these really long scatter lists or really big things to map. All our regions are going to be large. Today, all our regions are quite small. Right? They're the size of an I/O, which is 4K, 8K, 1 meg, that kind of thing. Those aren't very big. Now we're talking gigs, many gigs, terabytes, who knows. Note, 1 terabyte is 40 bits of addressing, right? Right? And 40 bits, that's a lot of bits. My length suddenly got really long. And Intel in 3D Crosspoint says they're going to cram 6 terabytes in the first generation. All right, that's 43 bits of addressing. That's 2 to the 31 pages. That is one heck of a scatter list. Okay, 2 to the 31 pages. I think my math is right. So it will favor region-based TPTs. If you have a page-based TPT, you're going to be in a world of hurt in this world. The DMA-MR, privileged MR, S-tag 0, a lot of names for it, cannot span all physical anymore. The DMA-MR really won't mean what it said anymore. The DMA-MR used to just say, I want all the memory. I just want a map to, all of physical memory. But now physical memory is not uniform, right? It used to be the worst you could have is a hole in it, right? Now you're going to have persistent memory, you're going to have ordinary memory, you might have PCI space, a memory bar on the PCI bus is going to map to this. So it would cross domains, and S-tag 0 really doesn't mean anything anymore. You can't commit to random things. You have to know exactly what you're committing to. The NIC needs to know. So because they require different durability properties and commit methods, I think S-tag 0 becomes less meaningful. And finally, the I/O size will change. They'll get very small, cache lines, bytes, I don't know, as well as very large, whole regions. That's going to be a big change. Implications number 2, these regions will be long-lived. There's a single setup, and they live for a while, okay? So these are not, brought into existence for the sake of one I/O or some short string of I/Os. These are there for days, hours, years, who knows. They won't be, there'll be a smaller number of regions needed, I believe, right? We won't need zillions of regions. We'll just need a few really big regions, 1 per DIM, 1 per file, 1 per virtual hard drive, I don't know. We might need more protection domains because we need to make sure that one guy doesn't scribble on some other guy. We need some better protection against this. So I think we might create more PDs, but way fewer MRs in this type of workload. The client won't need any regions. The client is never the target of an RDMA. He does all the RDMAs. So those regions will only be present on the server. We've totally inverted the picture. Today we need lots of regions on the client and lots of queue pairs on the server. Now we need, small number of regions on the server and nothing on the client, which is interesting. I'm not sure about the QP count. With parallel operation, we may still need a bunch of QPs. I don't think it'll scale as high as we do today. IRD, ORD, that's the incoming RDMA read depth and outgoing RDMA read depth. Those are the flow control limits for these atomic and RDMA read style operations. The commit operation may require its own queue. We may need a new thing, instead of an IRD, a CRD, I don't know. Because the commit latency is going to be longer than the read latency. So if the latency is longer, the delay bandwidth product is longer, which means we need more slots in the queue. So I think IRD, ORD will tend to grow if this proposal comes true. But my summary in the ARNIC resource area is that it's something of a seismic shift. You're gonna configure your ARNIC very differently in this world. And finally, there are verbs implications. The commit operation is going to have a potentially complex scatter list. The commit fail, if the commit fails, you didn't really lose data. You just didn't commit it to durability. So in my proposal, you might have noticed it whipped by, actually maybe it's in the internet draft that I'm about to mention. There's a status returned by commit. It's not a success or failure. It's not, failure in RDMA usually means close the connection. It won't close the connection. It'll return a status. So that's a slightly new verb behavior. And memory registration is going to be decorated. The verb is going to have to support very large offsets that it may not support today. And in particular, the verb may split the result. Right? If you try to register something that crosses boundaries, it may be able to return a short result. So that's a new behavior for memory registration. And finally, I mentioned it before, the DMA-MR is possibly obsolete. Right? I think with persistent memory in play, the DMA-MR may have no meaning. However, I'm not advocating for verb layer negotiation. That's a mistake, right? We'd write a whole new protocol in the verbs. Verbs are not protocol. Verbs are local only behavior. This is best left to the upper layers, which is what we do now. We should continue to do that. And second to last, actually maybe this is the last slide. No, second to last. External efforts. I just want to mention something that you may or may not be aware of. I've written an IETF draft with my colleague Jim Pinkerton. This is a link to the sort of history and metadata of that draft as well as the document itself. We propose these same requirements for the RDMA commit operation and also the local behaviors. We get into some detail on that. And try to write the document independent of the transport. The whole back half is about IWARP, but the whole front half, actually front 2/3, is transport independent. And I'm driving this in the IETF because it's a convenient forum for discussion. But I want to discuss it in other areas. And I was very happy a couple weeks ago, Diego and Idan Burstein had a presentation to the IBTA along these same lines. The SNIA NVM twig, of course, has been talking about this forever. I'm told that OpenFabrics DSDA is interested in this. I haven't been participating in that. But these are other very important efforts, and it's very important that we all agree, that we not fight with each other, that we not, diverge, right? These are really important things, and we need to have these dialogues across standards groups. Everybody with a dog in the game, should be involved here. And so I'm hopeful that this document, which I'll be updating soon, we were locked out of updating because of the IETF meeting. They freeze the IETF draft queue for 2 or 3 weeks. It's recently reopened, and we'll be updating this in the month of April. But I'm hoping that this document will help provide at least a basis for an open industry-wide dialogue on this topic. And to maybe motivate that dialogue, I just want to say, is this getting to the right semantic? How do we coordinate these discussions? How do we implement the hardware ecosystem? How do we drive consensus from the upper layers, the consumers of this thing, down into this requirement, right? It's really important to build a whole stack. You can't just do this a layer at a time. You've got to think it through. You've got to make sure that everything's going to work top to bottom. What about these new API semantics? What implications are there? Do we have a chance to think about these API semantics now while the APIs are still, the paint's not dry and stuff? What about the PM-aware file systems? DAX in Linux, DAS in Windows. If you were at the NVM Summit, you were very amused by the fact that the Windows architect and the Linux architect basically gave the same presentation. They could have swapped decks and said the same thing. There are very, very common problems here, and can we think across those lines? And finally, other semantics, or are these purely upper layer issues? Authentication, integrity, encryption, virtualization, which has some really interesting implications. Should those be part of this discussion as well? So I probably ran over, but I hope I didn't bore anybody. That's it.
Okay, slide 10. Push model. So push model will not work in HPC because we have a fundamental issue where we have a lot of clients and a few servers. So it's a many to few, or worst case, many to one, and push doesn't work. And that's why pull works so well that you see. So I grant you started off on slide 1 saying that this is geared towards enterprise and cloud. So my question is, not knowing enterprise and cloud, is every client also a server, or do they have some resources, a small pool that have data, and then a bunch of consumers? Because if that's the case, push is going to have an issue there as well. But if it's the Google HDFS or Hadoop or MapReduce on top of that, then sure. Or Azure, I should say.
Yeah. So
yeah, and here's the problem. The problem is in push, what you're going to hit is congestion on the last switch or at the NIC going in, right?
Indeed.
So that's the problem. You may not see it on the target because the target's dead, brain dead, but there will be a problem in the network trying to get to the target.
Congestion is the death of latency.
Yep.
Yes. If you need low latency, you need a well-managed environment. I definitely agree that push mode is problematic. I'm not viewing push mode as a panacea here.
Okay.
It brings its own set of problems. That's why I warn that, we've done this model, the model on slide 8, there's really good reasons for doing this model, right?
Yeah.
And we may not want to give this model up.
So the
will cost us.
The alternate is you do something like MIT did a couple years ago with FastPass, which is you ask a central broker first when you ask for a time slot to send, and then you guarantee no congestion. But that's an extra RTT right there, and that is not helpful to your latency.
Yeah. So
it doesn't probably scale to a data center.
So I think you're describing problems at the upper layer, and I believe the upper layer will have to think them through very carefully before it adopts them, right?
Well,
push mode is not enabled unless the upper layer implements.
Yeah, but once you have two clients, two different hosts, the upper layer doesn't help because they don't know what each other's doing.
Correct.
Okay.
Yeah, this is somewhat related. Like we talked in the hall about this, but push mode's been traditionally implemented with RDMA send. ICER has a mode of that. SRP has it. The NVMe Fabrics has it, because it has to do with how the target resources, provides the resources for the acceptance of that.
RDMA send with a credit.
RDMA send with the target indicates that it has the ability to consume a larger RDMA send with payload. That's been the sort of the traditional way that it's done.
Yep.
And one of the questions I had, thinking through this, because I know you mentioned, look, here's NFS RDMA, here's all these existing protocols that have this model of a combination of credited push and then pull if that credit doesn't exist. So those already exist. But let's say SCSI in your example of a push, are you saying that, for instance, the fundamental definition of a SCSI LUN is probably going to change to be a unit of memory region that is accessible from a remote? Because if you don't do that, how else is that going to work?
I think that's a possible implementation. I don't think that's the only one. Certainly if it's a virtual SCSI LUN and it maps to some virtual hard disk, it won't necessarily be a single memory region, but it will map to what is potentially represented by a single memory handle.
But why else? Why would you make that persistent if it's going to transition from that point into some other media? What's the point of making that persistent? Is that just extra work?
Well, the point of making it persistent is to give it a backing medium which has low latency.
But it's silent to the consumer, right? I mean, this is all sort of one-sided, whereas before, the operation was done and then there's a transaction which allows that to transition to some media. Because not all media is going to be, this class of performance, right? There may be capacity store that's going to, not be able to consume RDMA
Yeah, unless
rights.
this stuff is dirt cheap.
Yeah.
I agree with you. Yeah.
So you sort of see this as enhancing the storage protocols for persistent memory, sort of like adding this new flavor of, as opposed to completely eliminating the need to pull data and have the old model.
Well, to answer your last question, no, I don't see it as enhancing the storage protocols. I don't see it as modifying the semantics of the storage protocols one bit. I think what it will do is it will modify their transfer modes in ways that enable them to slide down the latency scale as the backing storage technology slides down the latency scale.
Yeah, but you mentioned ICER, adding enhancement to ICER to support a push. With this push,
I don't think
that's what confused me.
Yeah, because I don't believe ICER, as the protocol is defined today, would support push mode. None of these would.
Yeah, so that's
we have
enhancing
to
the
extend
storage protocol, is right, what you're
Well, yeah, but
suggesting.
it doesn't extend, it doesn't alter its semantics. It just changes its transfer model. The unsolicited data in, for instance, that doesn't affect the semantic of the data. It just affects the way it's sent. You may disagree.
I disagree.
Okay.
So if,
Go ahead.
sorry, go ahead.
Please.
So two questions. What's the typical commit latency, if you have thought about a commit operation?
I have no numbers for the typical commit latency because I don't have any 3D crosspoint or, any publicly available information for other alternative technologies.
Okay. So in general, we do bunch of writes and then one commit.
That's one model.
The other one is what you explained is write
Right
commit,
commit, right
write
commit.
commit.
Yeah.
Yeah. So the RDMA commit should translate to something a PCIe commit.
Ideally, by doing so, we would avoid having to invoke the remote CPU, which would reduce our latency. Yes.
Right. So I'm just thinking loud. At PCIe level, that RDMA commit needs to link up all the RDMA writes that would have happened, so that only those part gets flushed, not something else.
Well, yeah, indeed. The proposal for the commit currently takes a scatter list, which indicates the bytes which must be guaranteed to be durable prior to responding. Practically speaking, it's unlikely that the remote NIC will track each write and each byte of each region. And
Right.
it may commit data outside of the range that you requested.
Exactly.
It must commit at least the data you requested, but it probably will do more. Our expectation is that the initial implementation will flush everything that's dirty anytime in the past and say, okay, I'm good, right? Which is fine. But it might be quite expensive, particularly in a virtualized environment where you've partitioned this device and you have many unrelated data streams all requesting commit,
Exactly.
right? You could have 6 terabytes of dirty data. That'll take you a while, right?
Exactly. And so that's why I was again thinking loud. Instead of having a separate commit operation, like we have write, send with invalidate, write with immediate, should we have a write with commit as one write operation, so that what we just spoke is
Yeah, so we've given some thought to that. I certainly have. I don't think merging the two requests buys you anything other than saving a few bytes on the wire.
No,
The
not
two
on
requests can follow one another with the proper ordering semantic, and it's basically no extra cost. It's just like a post multiple.
Right. In that case, it would work if it's write commit happens. But if like 7 writes and 1 commit, in that case, we are putting a implication on adapter to link all the previous 7 writes.
No.
with the commit.
There's no message pointer in the commit. It's a region pointer in the commit. The operations themselves are not linked to one another. Now, they're ordered with respect to one another by the usual RDMA ordering rules. But that commit carries only the name and number and byte count of each region that it wants. It doesn't say the 5th last RDMA write that I sent is eligible.
Okay.
Right. So you could create all kinds of very strange, unrelated write patterns,
Yeah. So I was thinking write plus
just
commit.
like you can today. Yeah. I'm sorry.
Okay, thanks.
Okay.
So near the end, when you had the implications slide, you talked about new commit operation, and if I heard you right, you said that the status that came back could indicate a failure to commit that was not a loss of your data.
Right.
And I've been unable to think of any mode in which you failed to commit that doesn't correspond to some sort of hardware failure that's likely to also mean a loss of data. So what am I missing?
Well, so one of the more obvious models is the so-called NVDIMM model, where you have RAM on the front and flash on the back. And normally in an NVDIMM, when the lights go out, a little thing starts to flush the RAM to the flash, right? And promises, as long as the lights stay on, the battery stays charged, that the flash will contain the copy. But if you had a NVDIMM that would program on demand, that programming cycle could fail, but the data is still there in DRAM. I don't know that this is a compelling device or not, but it's within the realm of possibility, in my head at least, where the data was not actually lost, it just was not made durable. It's as if you had a server with a cache and a bad disk in the back end. The data is still safe on the server, it happens to be in the cache and it's at risk, but it's still there. Whereas the disk on the back end ain't ready to take it.
So I don't disagree with everything you've said, but if the disk in this last example is bad, then that's a larger container than the cache. And so have I not lost data that is outside the region that I was
Well,
trying
that
to
depends
commit?
on how the disk failed. Maybe it's just a bad sector and I was writing one bad sector. I don't know.
Okay. All right.
I don't think it's the domain of the RDMA layer to state how this behaves. I think this is the domain of the upper layer and the requirements of the workload. And so I don't want to overspecify it at the RDMA layer, right? You asked a commit of data that was already present on the server. The data's there, the commit failed, so the reply is only to the commit, right? It doesn't say anything about the state of the data. It just says that it's not durable. It's not yet durable.
Okay, so there'd be a set of different status that a upper layer protocol author would have some ability to reason about what they do next.
Yeah, the PM-aware library would have a recovery for it, yes. Yeah.
All right, thank you.
Yeah.
Regarding
Is that-
the memory translation resources.
I'm sorry, you're not coming through the mic.
Regarding memory translation resources, do you envision a few physically contiguous or at the bus address space regions?
Platform-dependent question, I don't know.
Yeah.
I really don't know.
Well, essentially, I'm asking whether the burden of translation should fall on the RDMA layer or on the non-volatile memory layer. So it seems that if I have some translation going in, like logical blocks on a flash device, usually it falls on the flash.
Right. And usually you expect it to come in units of, gigabytes and some big chunk, right? No holes in it, for instance.
Yes. So I'm asking whether do you see the RDMA layer compensating for different regions on, the storage medium, or?
I don't know. I mean, I think that's a hardware implementation question that the industry may want to think about. If it's really hard for network and RDMA adapters to do this, right? Maybe that's something that shouldn't be required. Maybe an IOMMU can help this. I don't know. There are other ways to create virtually contiguous regions out of physically discontiguous regions.
Okay.
Room for innovation. That's a good thing, I think. I love to leave room for innovation in any design, right? If you overspecify the design, who wants to build it? Philosophical, so I know. All right. Thank you.